Hello everyone, my name is Severin and this is AP Physics 1, Unit 1, Kinematics Review. So before you begin, there are a few essentials that you need to understand. The first is the difference between a scalar and a vector quantity. So a scalar quantity has only a magnitude. It's just a number basically, with a unit of course. So you could have 100 degrees Celsius or 20 meters or 300 newtons, while a vector quantity will be a scalar quantity along with a direction. There's a magnitude and a direction. So you could have 20 kilometers down, maybe for some objects falling very, very far. Or you could have 300 meters east. And now this leads us into the difference between distance and displacement. So distance is just a scalar quantity. It's just a number and a unit. So it's a distance something covers, some amount that an object travels. So 200 meters or 20 kilometers. Displacement, on the other hand, is going to be a distance along with a direction. So you know which direction the object was traveling in, whether it be north or south or east or west or at some angle maybe. So you could have 20 kilometers south. Or maybe you would have a unit of force, which, well, we haven't learned about yet, but like 20 newtons at a 45-degree angle. Or just for, let's say, somebody named Bob. This is Bob here. Maybe he walks at a 45-degree angle relative to some onlooker behind him, and then he walks 20 feet, or this is AP, so meters. He walks 20 meters at a 45-degree angle. So you have both your distance and you have your direction. And then this leads us into the difference between speed and velocity. So speed and velocity. So both of these amounts here are going to be basically rates of change. So speed, for example, speed will just be the rate at which an object's position is changing in terms of just distance. So it'll just be distance over time. So let's say you have some imaginary dog and he's named Spike. So Spike, let's say he runs 10 meters this way, and then when he gets there, he runs 7 meters back, and this isn't really a scale drawing, but so he's run a total of 17 meters in distance, because distance is just the amount that an object has traveled. But his displacement, 10 meters, 7 meters, his displacement is just going to be 3 meters to the right. And now we have distance and displacement, and let's say he travels these distances in 6 seconds. So his speed will just be 17 meters divided by 6 seconds, which is 2.83, I believe, meters a second. So that was his speed during these 6 seconds. He traveled 17 meters in 6 seconds. His speed is 2.83 meters a second. However, his velocity is based off displacement, which is just the amount that an object has moved from its starting position. So even though it might have moved, or its Spike in this case, might have moved 17 meters, he realistically only moved to 3 meters from his original position and 3 meters to the right. So if right is positive, then his speed is just going to be positive too. And so if you move 3 meters in 6 seconds, he just is moving at a rate of 0.5 meters a second to the right, so positive. And yeah, that's just that there is his velocity and his speed. So while velocity and speed might be terms that are used interchangeably in everyday life, they're actually different. Same with distance and displacement. This just a brief overcap. Scalar quantities, just a magnitude, just one number. Vector quantities, you'll have you'll have a distance and a direction, or just a magnitude and a direction. And then distance and displacement. Distance is just a scalar, just a direction, or just a magnitude. Sorry, distance is just a magnitude only. Displacement is a vector quantity. You have a distance and you have a direction. And then distance is just the total amount of change that an object has, a total amount of change in an object's position over time. So if an object moves up 10 meters and then down 5 meters and then up 12 meters, its distance traveled is going to be 27 meters. But for displacement, its displacement is going to be positive 10 meters minus 5 meters plus 12 meters. So its displacement is going to be 17 meters. So displacement is basically how much the object has moved from its original starting position, whereas distance is just how much the object might have moved between two times. And then speed and velocity are linked with distance and displacement. Speed is just the amount of distance total an object has covered over time. Velocity is just the amount of displacements an object has experienced during an amount of time. Okay, so our next topic here is going to be acceleration. So acceleration is basically just a change in velocity. So it's the rate of change of velocity. So this means acceleration or an accelerating object can either be changing directions, maybe it switches from moving right to moving left, or it can be changing speeds, maybe it can be speeding up or slowing down. So according to just everyday language, accelerating is just increasing speed. But by the physics definition, a car turning a corner is accelerating because it's changing directions. Or even a car slowing down is also accelerating, even though you might say it's decelerating, which would still be appropriate in a physics definition because it is slowing down, but it is accelerating. So acceleration is measured in meters a second squared because it's just meters a second over seconds. So let's say we have Spike, our friendly dog, and he's moving forward at 5 meters a second. So forward direction is just positive. And then let's say he speeds up. So now he's going to be moving forward at 10 meters a second. And let's say he changes his speed from 5 to 10 meters a second in 5 seconds. So we basically just have to divide velocity by change in time. Change in velocity by change in time. So his velocities is going to change 10 minus 5 meters a second. And then the time is going to change 5 minus 0 seconds. So we have 5 meters a second over 5 seconds. So his acceleration is going to be 1 meters a second squared. He basically increases his speed by 1 meters per second every second. Okay, so our next topic now is going to be position and velocity versus time graphs. So we can use graphical interpretations of an object's movement, such as this position over time graph, to determine things such as velocity, speed, and acceleration. Right here, we have a position versus time graph. So this is showing, let's just use an example of Spike again. This is showing Spike's movement over time. So he moves 5 meters in the first second, and then to 15 meters in the next, and then back to 10, and then up to 25, and then stays there. So usually upward and rightward on graphs are positive directions. So Spike will be moving right here, and then left here, and then right here. So the velocity of Spike during these in these time intervals will just be the slope of the graph, because that is the amount that his position is changing by over time. So we can find his velocity, let's just say over this time interval from 1 to 2 seconds. So he ends up at 15 meters, and he starts at 5 meters, and then this is over the time interval of 1 second, from 1 to 2 seconds. So his velocity will just be 10 meters a second. And then right here you can see he moves backwards because his velocity is negative here. He's moving backwards from 15 to 10 meters. So even though the graph isn't under the x-axis, his velocity will be negative because it's slope. And then we can also find the distance he has traveled and the displacement over this time period here. So his displacement is just going to be his final position minus his initial position. So he ends up at 25 meters to the right here, and he starts at 0 meters here. So he's just going to have moved a total of 25 meters. His displacement will be 25 meters. His distance traveled, however, is just going to be the sums of all the amounts that he's moved. So basically he's moved 5 meters in this first second, and then he moves 10 meters to 15 meters. He moves 10 meters in this second, and then he's going to move 5 meters backwards here. So remember, when we're looking at distance, the direction he's traveled doesn't matter. If he's moving in the negative direction, we still add it up. And then he moves from 10 to 25 meters here, so 15 meters, and then he's at rest here. So his total distance traveled, Spike's total distance traveled, will just be the sums of all the amounts that he's moved. So it will be, his distance traveled here will be 35 meters total. Okay, so now that we've gone through that, let's look at a velocity versus time graph. Okay, so now that we've looked at position over time graphs, we can take a look at velocity over time graphs. So I've drawn out a simple one here. And so the velocity at different points along this graph will just be the y value of the graph. So the velocity of, let's say that this is, we can just say this is Spike again, just for the sake of consistency. And then so Spike's velocity at time equals 1 second will just be 2 meters a second, and then Spike's velocity at time equals 3 seconds will be negative 3 meters a second. He's gone, the velocity graph has dipped under the x-axis, so everything down here is negative. So we can find his velocity obviously at different points along this graph, but we can also find his acceleration, because the acceleration on this graph will just be the slopes at different points. So we can find his acceleration over this time interval 0 to 1. We have a final velocity of 2 and an initial velocity of 0. So 2 minus 0 meters a second, over 1 minus 0 seconds. So Spike's acceleration over this time period here, 0 to 1, will just be 2 meters per second squared. And then we can find, let's just take another example down here. So Spike's final velocity down here is -3 meters a second. And then his initial velocity is going to be -1 meters a second. And then this is over a time interval 2 to 3 seconds. So his acceleration here will just be -2 meters a second squared. And we can also find the distance that Spike has covered from this graph. We can find the distances and his displacement. So this is just going to be the area under the graph. So we can find his distance traveled from 1 to 2 seconds here by just finding this area, and then we're going to subtract this area. That will be his displacement. If we want his distance traveled, we'd add both of them. So we can find, this is just a triangle here. So 2, which is the height, times 1, which is the base, divided by 2, plus, and then this is a bit tricky, slope is -3, so the base is 0.66 or 0.67, and then times 2 over 2 minus 0.33 times 1 over 2. We can just put that into a calculator. So 2 divided by 2 plus 0.67 times 2 divided by 2, and then minus 0.33 divided by 2. So Spike's total displacement from time 1 to 2 seconds will be 1.51 meters. So this will be positive here because Spike has traveled to the right. In total it's positive because he's traveled further to the right than he has to the left. And so we can notice here that when the velocity graph is over the x-axis, when the velocity graph is in the positive area, Spike is always going to be moving to the right. Even if the velocity graph is going, even if the slope of the velocity graph is going down like this, even if it's negative, he's still going to be moving to the right until the velocity crosses 0 and becomes negative. Then he's moving to the left. And so he will still have a positive displacement. He will still have a net movement of towards the right until this area here and this area, some area under here, are equal. So maybe let's just say imagine that some point 2.7 seconds. At this point, these two areas are equal to one another. So he will have moved right over this time here, and then he will have moved left back to his initial position at in this time here. So our next important topic here is going to be acceleration versus time graphs. So let's say this is Spike's acceleration over time. So we can see he's accelerating, he's speeding up here, and he's still accelerating here, but then it dips below acceleration's value dips below 0. So now he's accelerating backwards until here, and then he begins accelerating in a positive direction again, and his acceleration is increasing here. His acceleration is increasing here, decreasing here, decreasing even more here, and then increasing here, and then he's accelerating here at a constant rate. So let's break this down a little bit. First, the area under an acceleration versus time graph is going to be velocity. So as we can see, I intended this graph to be to scale. So velocity 2 is going to be smaller than velocity 1 and velocity 3, obviously. So that means that spike is always going to have a positive velocity over this entire time period. He's always moving to the right. He's always moving to the right because his velocity, let's say for here, his velocity is obviously going to be positive because the area under the graph is positive. But then in this time period, right here, at this point in time right here, we can find his velocity by just having v1 minus v2, which is going to be greater than 0. So he's still moving to the right. His velocity is still greater than 0. And then obviously when we add v3 to, that's just going to be greater than 0. When we add v3 to the equation, his velocity will still be more than 0. So he's still going to be moving to the right. Throughout this entire time period, spike always has a positive velocity. He's always moving rightward. Even though he's decelerating at times, even though right here he's decelerating, his acceleration is negative. So with respect to how he was moving before, he's decelerating. But he's always going to be moving to the right, which is an important distinction to make. If you have a car moving at 100 kilometers an hour, and then the car begins decelerating, that doesn't mean the car moves the other way. The car is still moving to the right, or whatever way it was moving before. The car is still moving in the positive direction until enough time passes so that it eventually starts moving in the other direction towards the direction of its acceleration. So let's say we have a velocity over time graph here. Sorry, that's a bad time, seconds, velocity, meters a second. And then we'll overlay acceleration on this as well. I'll draw it in blue, hopefully you can see. So let's say our object's velocity, let's extend this down here too. So let's say our object's velocity is going to be increasing here, and then it's going to have a sharp decrease here, and then increase here, and then just slowly decrease here. And it's a bit hard to see, I messed up the graph a bit. But now let's find the accelerations at these different times. So acceleration is slope of velocity. So slope here is positive. So acceleration will be something like this. And then it'll stop here. And then the acceleration, I drew that a bit too far. And then the acceleration here is going to be negative because the slope is negative as well. And it's going to be, the slope is very steep, so acceleration will be quite a little, will be larger than before. So we can have, let me draw some lines so it's easier to. And then now acceleration is going to be positive here because velocity slope is positive, and it's going to be a bit steeper than before, and this for a short time. And then right here we can see velocity slope is 0. Velocity doesn't change, so acceleration is just going to be on the x-axis like this. Acceleration is 0 here, and then velocity right here is decreasing, negative slope. So it'll be a negative acceleration value, just something like that. So as we can see, at certain points, acceleration can be negative while velocity is still positive. So right here, for example, velocity is positive, so the object is moving this way, but acceleration is negative, so it will be decelerating or accelerating in the other direction. So it only starts moving in the other direction when velocity dips below 0. Then right here, right here, velocity and acceleration will both be in the negative direction. And then now that we've covered that, we should talk about acceleration due to gravity. So acceleration due to gravity on planet Earth is 9.8 meters per second squared. In AP Physics, 10 meters per second squared is often an acceptable approximation, unless stated otherwise. And when solving equations, kinematics equations, or any kinematics equations, assume no air resistance. So air resistance does not exert an effect on an object's fall, although in real life, air resistance is the reason for why objects fall at different speeds. So if you take, let's say, some tissue paper, and then you take an eraser or something, and you drop them both, the eraser obviously hits the floor faster, right? It drops straight down. The tissue paper kind of floats there. But it's not because acceleration exerts a different influence on different objects. The reason why objects fall at different speeds is not because gravity has a different effect on them. Gravity is always there, it's always constant, and all objects should in a vacuum fall at the same speed with the same acceleration. However, in real life, this is different because there is air resistance. So the air will catch the higher surface area of the tissue paper and slow it down more, as compared to the eraser, which doesn't have as much surface area. So it's not because objects have different masses or are lighter or whatever. All objects should fall at the same rate. And so assume that all objects fall at the same rate, unless stated otherwise in the problem. And now, another important distinction to make, or another important thing to know, is components of an object's motion are independent of one another. So let's say I have Joe here. Okay, Joe's playing baseball, right? So he has his baseball here, and let's say he throws it. He just throws it up in this direction. So if you know a bit about vectors, this this vector of the baseball's motion can actually be broken into two components. So you have the x component, or the horizontal component here, and then the y component, or the vertical component here. So let's just call this velocity of the ball, and this will be velocity y, and this will be velocity x. So it's important to know that objects with objects moving, their components of their motion are not affected by one another at all. So this object's velocity, horizontal velocity, will not change due to changes in its vertical velocity, and vice versa. So we can draw out the path of the baseball's movement. It'll make a simple arc here. Okay, and then we can put the components of its movement on this arc in different locations. So basically, even though this ball is changing velocities, its vertical velocity is changing, its horizontal velocity doesn't change at all. There's nothing there to change its horizontal velocity because we're assuming there's no air resistance. So without gravity, theoretically, you just throw this ball, you just go straight. It would go on forever. It wouldn't fall down because its vertical velocity doesn't actually change at all. Its horizontal velocity, however, changes due to gravity. So it's going to be heading up with this original vertical velocity, but then acceleration starts to drag it down, and then it falls back to the ground here. So we can, if we have an angle at which the ball is thrown here, we can find its vertical and horizontal components of velocity by just using trig functions. So horizontal velocity is just going to be its velocity times the cosine of the angle of its movement, and then its vertical velocity is just going to be its velocity times the sine of the angle of its movement. Okay, so now that we've gone through all the fundamentals, let's get down to the nitty-gritty kinematics equations. So first of all, let's start with basic speed, velocity, all that good stuff. So speed or rate, r, equals distance over time. So just speed, or well, rate as it's called in physics, is just going to be the distance an object travels divided by the time it takes to travel that distance. And then velocity, average velocity specifically, will be an object's displacement over the change in time, the time it took to make that displacement. And so this triangle here just means change. So this will just be x sub f, x final position, minus initial position. And then acceleration is just going to be change in velocity over change in time. And this will be technically average acceleration. And now that we know that, we can start on the first kinematics equation. First of 4. There are 5 technically, but 4 is all you need. So average velocity equals change in x over change in t, displacement over change in time. And we can rearrange this. So change in position, displacement, equals velocity average times change in time. And so velocity average, if you've done your algebra homework, will just be final velocity plus initial velocity divided by 2. And then we multiply by time. So this is going to be kinematics equation 1. I should write 1. Okay. Now that we've done that, we can start with the next equation here. So acceleration here, you could write average or not, it doesn't matter too much, equals change in velocity over change in time. So now we can rearrange this to be acceleration times change in time equals change in velocity, which is just final velocity minus initial velocity. And now we're going to just rearrange this to find final velocity, and it's just going to be initial velocity plus acceleration times change in time. And this will be average acceleration. Acceleration has to remain constant for all of these equations, so actually this won't be average acceleration because it's always just going to be, acceleration will always be the same. Unless you're in a more advanced physics than AP Physics 1. So here is equation 2. Okay, now that we've done that, let's move on to equation 3 here. So in equation 3, we have average velocity equals displacement over change in time, and then this will just be final plus initial velocity divided by 2 equals displacement over change in time. And now we have the sum of final and initial velocities will equal 2 times displacement over time, and we can multiply by change in velocity divided by change in velocity, which is basically just 1. So this is legal. We're not breaking any math laws here. So velocity final and velocity initial, the sum of, will equal 2 times displacement over change in time times change in velocity divided by the difference between final velocity and initial velocity. And now that we have that, we can multiply both sides by this here. So this basically just moves over here. So final velocity plus initial velocity times final velocity minus initial velocity equals 2 times displacement times change in velocity over change in time. Okay. Now, if you've, again, done your algebra homework, you know that we can simplify this into just final velocity squared minus initial velocity squared equals 2, and then we can see here, this is familiar. We can check back and acceleration is velocity, change in velocity over change in time. So we can plug in acceleration and substitute acceleration here. So 2 times acceleration times change in x, don't forget that. And so now we have an equation to find final velocity from initial velocity, acceleration, and total displacement. So final velocity squared equals initial velocity squared plus 2 times acceleration times change in x. And that is going to be our third equation. Okay, now fourth equation here, fourth and final one. So this one is going to be a bit more tricky because we need a graph here. So let's just draw out a quick sketch. So this is going to be a velocity graph, velocity over time. And so we can see that the areas under this graph, which, remember, this is a velocity over time graph, so the area under the graph is going to be position. So we want to find our final position, basically, or, well, displacement, you could say. So we have, let's denote this here as initial velocity and this here as final velocity. And then let's just say this is change in time. So we can look at the area and find the areas under here to find displacement. So this area is a rectangle, and the length of its two sides are the magnitude of initial velocity and time. So the area of this is just initial velocity times time. And then here we have a triangle. So we know the area of a triangle is 1/2 base times height, right? And then the base here, well, the base could be either the difference between velocity final and velocity initial, or time, depending on how you look at it. But for simplicity's sake, we'll say the base is going to be time, change in time. And then I've already spoiled the rest, but height is just going to be the difference between velocity, final velocity, and initial velocity. Okay, so now we know that the area under a velocity graph is going to be displacement. So we can say displacement, change in x here, equals the sum of these two, because that's just finding the area under the graph. So velocity initial times change in time plus 1/2 change in time, velocity final minus velocity initial. Okay, and now we can notice here, this is going to be change in velocity. So displacement equals velocity initial times change in time plus 1/2 change in time, change in velocity. And now we can do something interesting here. We can multiply here by change in time over change in time. So what we have is displacement equals velocity initial times change in time plus 1/2, and then take a look here. This is just acceleration because it's change in velocity divided by change in time. So, and then we have a leftover, we have 2 leftover change in times. Those are both going to be in the numerator. So 1/2 change in time squared times acceleration. Or restated, final position equals initial position plus initial velocity times change in time plus 1/2 times acceleration times change in time squared. Quite the mouthful. But this is going to be our 4th and final kinematics equation. Alright, now that we've covered all the basics and we have all that down, I'd like to cover a few common misconceptions concerning kinematics before we move on. And there are 2 links in the description with many more misconceptions. But here's the first one. So position, velocity, and acceleration are all dependent on the frame of reference of an observer viewing an object. So let's say a man is sitting in a moving car. In the man's perspective, he isn't moving, he's sitting in the car. In that system of the man in the car, he has a velocity of 0, an acceleration of 0. He's just staying there, his position is not changing. But to an outside observer, the car might be turning a corner, or speeding up, or slowing down, or otherwise moving in some way. So to them, the man's velocity is non-zero. His position is changing, his acceleration might be changing, it might be non-zero. So the same kind of concept can be observed from a plane. So you're sitting in a plane and you're looking down at a car moving on the road. Now that car might be moving at, like, say 150 kilometers an hour, right? But compared to the speed of the plane, that car is moving very slowly. In fact, compared to your movement, the car is moving backwards in your frame of reference because the plane is just that much faster. So to the car, however, the car could be observing the background scenery moving by really fast. So the car has a changing position. It has a non-zero velocity. The plane above it, however, is going much faster than them, but not as fast as it is actually moving. If the plane is moving, and I don't even know how fast planes move, but if the plane's moving like 600 kilometers an hour, the car is moving 150 kilometers an hour, to the car, that plane is only actually moving 450 kilometers an hour. But to the actual plane itself, concerning the surroundings, that plane's moving at its actual speed of 600 kilometers an hour. So that's one of the misconceptions I wanted to touch upon. So another small misconception is that objects in free fall have to always be moving downwards, and this isn't true. An object in free fall simply means that the only acceleration that the object is experiencing is just downwards. So it's only gravity acting on it. So you can throw a ball upwards, and even though it moves up for like the first half of its movement, the whole entire time it's moving up and then down is that ball in free fall, even though it's moving up initially. So free fall doesn't depend on the velocity of the object, whether the velocity is up or down or left or right. It only depends on the acceleration being down, being only gravity. Okay, now this is another very important misconception, probably the most important one out of all these three. This will come up on like AP Physics tests and stuff. So when, let's say a platform is moving, and then there's someone standing on the platform and they throw a ball up, and then it falls back down into their hand and they catch it. So this is what will theoretically happen if there's no air resistance. You are moving on a platform, you throw a ball up, it falls straight back down. In your perspective, it falls straight back down, and then you catch it. However, if there's air resistance, it's basically like the same thing as someone throwing something out of a car, right? You throw it out, like say it's just a cigarette, or you're like littering in a piece of plastic. Well, cigarettes are littering too, but you throw it out of the car and it flies back. That's not because suddenly the object just like loses all the velocity that it had in that car. It's because air resistance pushes it back and causes it to suddenly just fly backwards. So theoretically, if you were to just be in a car driving forward and there's no air resistance whatsoever, and you just throw the ball out the window, then the ball from your perspective just falls straight like forward and then hits the ground, and then it would like stop moving and it would fall. It would like just and then the car would speed past. The ball would still like be moving alongside the car. But this isn't how it really works in real life because there is air resistance. So if you have a problem on an AP Physics test and it says some object is like thrown up and down or something on like a moving platform and there's no air resistance, then that object is not going to have moved relative to the platform in any like horizontal position if it's simply thrown straight up. If it's thrown with some kind of horizontal velocity, then the story might be different. But that's the last misconception that's really important. And like I said, there are 2 links in the description with more misconceptions that you can review if you like. I highly recommend it in case you don't understand it. I just covered maybe like the 3 most important ones. But thanks for watching, and I'm going to be posting a problem solving video soon, solving like 5 problems. If you want more help, then tune back in for that. Also, if I made a mistake or you feel I should have added something, please don't hesitate to comment. I have lots of room to improve, obviously, and I'd really appreciate any feedback you might have, no matter how small it might seem. It still is important to me. I left more than just the misconception links in the description. There are more materials, so yeah, please check down there. And good luck. I hope to see you in the problem solving video, and have a great day.